Good morning, or afternoon, or good evening, whatever the case may be. This was one of the graphics used in one of our readings this week, and I thought it was an interesting representation, simple drawings of people transacting, people having cards swiped, something representing Starbucks, I suppose, or Panera. Somebody has purchased some kind of lamp and is about to plug it in. Father taking his daughter through some kind of shopping environment. Somebody just planted a or purchased a plant or is planting a plant, or maybe she's just gone and done something online to look up how to fertilize the plant. It's hard to tell, but these are all transactional in nature, uh, hence subject to generating data. The crux of data and data management is, of course, the database. You can't have big data. You can't have data warehouses or data warehouses. Do you say data or do you say data? I hear it said both ways. Anyway, businesses rely on their database systems for all mission critical information, probably all but the very smallest businesses. I can imagine there are some that kind of use paper ledgers and pencil still, but any business of any size that employs people has to interact with government or government forms, has to do any kind of business online, has pretty much got to be a data business. So information needs to be complete and up to date in a database. Databases are invaluable in most organizations. Users can retrieve, alter, and delete data if they have appropriate permission, and they can save the modified data. Now, my own small business, I have a combination of spreadsheets, QuickBooks, and tax services. I don't necessarily think they comprise a database management system, but they do involve some level of databases. And my client database is essentially spreadsheets, which are, as we will learn, flat file database systems. So uh, that's just full disclosure. I, of course, work for other companies, including two universities, and I am part of their database systems as an employee and as a teacher. So, employee and a teacher, not the same thing. In one case, you can be an employee without being a teacher, but in the case of being a teacher, you have to be both an employee and a teacher. And they are actually two different ways that the database has to handle people. So there's that issue in databases. Databases help keep information updated, accurate, organized, and in format that is usable, and ultimately it will be storable and usable and a data warehouse situation for future analytics. Uh, Broad definitions: formally arranged set of persistent information that can be accessed and modified. A collection of interrelated data, second bullet there. Uh, a database object is a named data structure that is stored in the database. A database model refers to the way in which a database organizes its data to pattern the real world. We'll get into that in a few minutes. Formally arranged basically means that the data is in a particular way. A relational database stores the data in a tabular way, which means multiple tables, actually. A flat file database, such as my Excel spreadsheet, is stored in a kind of single file that is not interrelationable with other tabular systems right now. So maybe I'll convince myself to change that. Persistent information means that the information remains intact after the program accessing it has terminated. So the database can operate and provide simultaneous information on similar customers to different workstations at different times. In other words, a customer file, for example, can be being accessed by the billing department and by the doctor treating a patient simultaneously. So a user can access and alter information, save it, and a customer file can be accessed from a database, updated with the latest purchase receipt, etc., and saved. Uh, we saw, or if you haven't seen it and watch later, the data warehouse video. This would be the transactional end of that scheme where we see the data warehouse modeled. Database management systems are how we take care of all this. DBMS is the common abbreviation, and database properties feature layers of data abstraction, physical data independence, and logical data independence. So what do we do with databases? We use them to specify types, structures, and constraints. We construct them to store our data, and we manipulate them. We query, we update them. This has to be done. And we use them to generate reports, kind of a primary level of data analytics. Databases have the unique ability to present multiple users of the data with their own distinct view of the data. Think of it this way. If you are say a multi-outlet dental practice, you have data that is visible to your customers who have accounts and can access their accounts online. You have views that are available to your dentists, your doctors, your practitioners who treat the patients, and you have views that are available to people out front who check people in, and you have views that are available to people in accounting, people responsible for managing the account, so to speak. Those are the external layer. The logical layer is the external schema. This is the way that the databases are set up and maintained and implemented. The physical layer are the actual files, the tables that contain the data. A user does not really need to have any knowledge of how or where the data is stored. However, many PC-based databases for small companies and the like require that the user locate a physical file. Server-based database management systems have physical files that are managed automatically. So the user at a terminal or workstation or point of sale device does not have to worry about where files are located. The physical layer actually refers to the data files, the files that are accessed ultimately at the other end by the users. Logical layer refers to the first two layers of extraction. They are abstract data structures assembled from the physical layer as needed. This first layer is called the schema, and that basically is the organization. Which files relate to which table. And this is ultimately accessed at the top level, which we'll see in a minute, by the user. Logical data independence is key. That's the ability to make changes to a logical layer without disrupting existing users' processes. In other words, if the data if somebody's record is being updated, it doesn't necessarily affect or fight with any changes that are being made in an account that's being interacted with, say, at a workstation or at a point of sale device. The external layer is the second level, and it's composed of user views called the subschema. These are basically the terminals, workstations, point of sale devices, ticket windows, you name it. Here's a look at layers of abstraction from the view of two people using information databases related to horse racing. User 1 has a look at certain things, and user 2 has a look at certain things. If you take a look at this and study it for a second, which we won't do here, you can come back and do that, and you can do that with any of these slides, is user 1, in my opinion, is probably some kind of breeder or trainer, whereas user 2 might be somebody that's involved with the racing or betting end, or perhaps some kind of sports reporter. She's looking at information on her screen relating to certain things that come from certain tables in the database relating to race ID, the date, the horse ID, the name, the owner, and all that. Whereas the top user, user 1, is looking at owner, some of the same stuff, but he's looking at other information that's put together by his end user view of things. So different views, same database. There are, as we mentioned at the beginning, different types of databases. The main things we're talking about here are flat file and relational models. They have the same genesis, and actually relational databases came from the notion of flat files and how to make them more responsive and less redundant and avoid some of the problems with flat file databases. These were the first attempt at computerizing the traditional manual filing systems. And as I've mentioned myself, my database is basically Excel spreadsheets. Uh, this system has its advantages in that it provided an organization that wasn't possible when people were using paper systems, and access and the ability to update easily. But it has a simple structure, and it can't contain multiple tables like a relational database can. Here's an example right there. This is a database relating to sports cars. Problems are records are stored as line of text. There's no flexibility. Styles are in various locations. Oftentimes with flat file databases, you'll find customer names referred to one way in one file and another way in another file. There's conflict between job numbers, project numbers, invoice numbers, and things like that. There's a lot of redundant work required to maintain flat file databases. So those are just a few of the issues. Relational database, as I mentioned before, is the primary unit is the table. Tables can be used independently, or joins can be used to combine tables, and that's what usually happens. Relations are defined using primary and foreign keys, and every table has a primary key, and then some tables have foreign keys where redundant or where information is entered from other tables that are critical to that data field. Data structure can be easily changed. They're very fast. Users don't need awareness of physical storage. In other words, when you're working at a terminal at your computer, accessing a database, or when you're working at the front end of a doctor's office, anywhere you're using it, you're using the same databases as others in the organization without any real awareness that they're using the same database. So everything's very transparent to the owner. Easy programming. These are all based on something called SQL, which is Structured Query Language. You're probably familiar with programs and application names anyway that use SQL. Here's an example of a relational database. Each of these squares, rectangles, represents a table. And tables are developed for entities. An entity is a way of referring to elements in a SQL a relational database where, well, an entity is what it says. It's an entity. It can be a person. It can be a single invoice. It can be a single project, usually identified by a project number. It can be a department, it can be a client or customer, and usually that's one of the key entities in any database, or patient, depending on how you want to label it. In this case, the database is based around a survey, presumably done by some survey organization. What you see there are a kind of a system of lines showing the relationships. And one way of noting the relationships is to use one and then those multiple little double O's that represent, in this case, many or more than one. So a better way to show entities in one that's more common is to use cardinality, which I'll show you in a minute. Note here, respondent, he or she is one respondent that is doing one response at a time. The response here shows that there are many responses. Here's another way to do it. This shows cardinality a little better. There are several different ways to indicate relationships in an enterprise resource diagram, ERD. Here you see little hash marks right next to doctor. And over by patient, you see that little zero with what looks like a bird claw. That's one way you can kind of remember the term cardinality. That little claw thing really represents between 0 and many. The O represents 0, or that little circle, and the three-pronged little connector point represents many. So we have various types of relationships in an enterprise resource diagram. We have one-to-one relationships, the two straight lines. We have one-to-many, which would be a straight line with the little bird claw, see down at the top of nurse. We have 1-to-0. You sometimes have 1-to-0 relationships, or 0-to-1. I'm not putting all the reversals on here. Many-to-many is indicated by M:(n). And then you have many-to-0. And you see that in a couple places on this diagram too. So here we have a room. A room up there, the blue square, can either be occupied by 1 or 0 patient at a time. It can also be 0 to many patients are served by that room in the course of a single day. A doctor, a primary care physician, has a one-to-one relationship, or the patient has a one-to-one relationship with his or her primary care physician. And the primary care physician, or the doctor, they're not all primary care physicians, that's why this table is this way. The doctor will serve between 0 and many patients as a primary patient. Why the 0? Well, some doctors are interns, so they don't really have key responsibilities for a single patient. And some doctors at some organizations do research, and they're in a non-patient kind of role. If you look over where it says nurse, you have kind of a circular, nurse connects with nurse. And this happens in a lot of departments where similar people or similar types of employees have reporting responsibility to others. So some nurses are supervised by other nurses and some aren't. That's the 0-to-1. And some nurses supervise a number of nurses, or some don't supervise any. That's why you have that little circular connection thing. It looks confusing, but it makes sense in drawing out an ERD, an enterprise relationship diagram, rather. So we focus on relational databases because they're more established. They are kind of the de facto standard in industry now, in any type of organization. You guys, we are all part of multiple databases as customers, as employees, I mentioned this a little earlier, as members of the Keuka College organization. We are all in the database with our name on a table as an instructor or as a student or both. I know one or two people in this class are employees, so the databases for colleges are all organized and schemed out, so to speak, to handle the fact that people can be employees and students and instructors all at once. Something that's got to be organized and dealt with and thought about in the diagramming and the setting up of the schema, so to speak. So those are some key points about why we focus on relational databases. Here's a slide that kind of tries to contrast flat file versus relational databases. And this is a kind of a good way to look at it, how things are set up. But I know that when you do a enterprise relationship diagram for a relational database, you also have to have a data dictionary. So the data dictionary kind of defines what everything is, what it means, how is it a number, is it a number letter combination, is it a name, characters, that sort of thing. So you still have to do this in a relational database, but the relational database, as it shows here, connects, like we did on some of those other diagrams, these various entities which are on tables. Just some key terminology here: concurrency, integrity, redundancy. Concurrency is probably the one that's least clear on the surface. It describes management's ability to handle simultaneous queries against a single set of tables. So that's important. Something that's really kind of difficult with a flat file system. So there's the descriptions also for integrity and redundancy. That's it for this one.